All right, what's up, guys? How's it going? Just got back from a long walk with my dog. It's Tuesday morning, 10:24 a.m. So that reminds me that you guys got an asynchronous problem set today. So section 2.4, day one, angles of a triangle. These are the examples of the problems we're going to do. We're just getting, this is just the examples of the problems. If you're curious what all the problems are that you have to do, they're right here, right? They're listed on today's assignment here. And remember that we have the schedule. Oops, not Geo schedule. We have it right here. Okay, so we have it right here, so you can see every single problem. You're probably fast forwarding on to the examples right now, but yeah, just to remind you that we're kind of writing down everything that we've learned so far. Or you should know, right? You should always go back and recheck this. Be like, did I really get all this stuff here? If not, is there anything I need to reread or ask about in case I'm not sure, like what the symmetric property of congruence is, other things like that. Okay, it's an important skill to have, to kind of always be looking backward, but then turning the page, seeing what's coming up before us, and seeing, and then re-looking at stuff from the past. Okay, so now I'm just kind of buying time to show you that I list out. Oops, I went too far. I list out, and there is one person viewing this with me as well. Hello, person. My computer's slow. Sorry, guys. Here under Thursday, October, was it 22nd today? Here's the problem set. So numbers 4 through 11, classroom exercises, 2021. Numbers 1, 4, 13, 14, 15, 19, 22, 27, 31. Now, if you feel like you're getting all of this and whatnot, this should take you definitely less than 40 minutes to do it all. If you're struggling with it, right, that's fine, right? This is a class where we work through struggle, we grow. You might not get to every problem, but try to do as much as you can. You want to get exposure as much as you can, because my goal is to show you as much as I can about geometry this year. I know that's we don't have as much time together this year, so trying to show it all to you without taking up all of your time. So try working on this for about 40 minutes today. All right, without further ado, let's go ahead and get into it. So I'm going to do for my classroom exercises, I'm just going to do 3 of them as examples, and written exercises just 2, one of which is a proof, so this will take a little bit longer. Starting with number 7 here, it says, explain how each corollary of theorem 211 follows from the theorem. Okay, so remember, if we have a theorem, right, and then we want to get something to follow from it really quickly, like kind of like 1 step, 2 steps, 3 steps, right? We're trying to get something to follow with it, like that would be called a corollary. So if we can string together like 1 to 2 to 3 more reasons on top of this theorem right here, right, on top of this theorem to justify another fact, right, we're going to call that other fact a corollary, right? A corollary is a theorem, right? So it is a fact as well, a proven fact that is proven very quickly, right? Very quickly to another theorem. So these here are very much, right? Very much, this statement here and this statement here are very much related, because this one here is based off of the theorem here. Okay, so corollary 1, let's review it again. We don't pay attention to the numberings of things, so I'm even gonna cross this out. You just should know the fact, right? This is a fact we proved. The sum of the measures, the angles of a triangle, is 180. That's always gonna be the case for any triangle. Add up the measures of the 3 angles, they add up to 180 degrees. Another fact as well involving 2 triangles, and maybe I'll sketch this out real quick. Boom, 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 and boom, boom, boom. I'm trying to draw these scaling, nothing kind of special about them. Let's say, pretend that these are obtuse. Looks kind of right, but anyways, nothing. Trying to draw them scaling, and none of the angles are congruent to one another. Just kind of show this here. All right, so this is the statement here. This is the proposition, the if-then statement, the conditional statement. Oh, I'm saying all these crazy vocabulary words. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are congruent. I didn't save much space for me to actually write out my answer, so I'm going to redraw this real quick. Maybe right here. There we go. Let's keep it more right now. And yeah, maybe I'll actually do this one smaller. It doesn't say that the triangles need to be exactly the same. They just need to have the same angles here. So I drew this kind of messed up here, but whatever. We're going to go with it here. All right, 2 angles of one triangle congruent to 2 angles of another triangle, and the third angles are congruent. So maybe I'll mark it up real quick. Let's say that this and this, these are congruent angles. They don't really look that congruent, but whatever. Let's just say they represent congruent angles. So these represent the congruent angles, so they have the same measurement, right? They have the same measurement. And let's say this one up top here, that's congruent to this one up top, right? They have the same measurement right here. So what this theorem is telling us, once we think through the proof of this, and I should have explained this on the lesson that you saw last night, is that this one here, we're going to be able to deduce that these angles would have to be congruent to one another. Again, these are just diagrams here. I didn't draw the triangles completely accurately. This is, again, just practicing our reasoning right here. Okay, reason for this. Okay, reason for this. So since the sum of the measures, right, we want to include this in every one of these ones that we have, numbers 7 through 11. Since the sum of the measures of each triangle, because we'll talk about both of them, is 180, and okay, all right, maybe we can do this maybe actually. We can maybe assign some variables here. That's actually probably the easiest way to show it. Okay, let's pretend, or let it be, right? Let it be, the Beatles sing that better than BTS. Let's pretend that one angle, oops, get out of there. One angle in both triangles measures x degrees, and another angle in both triangles measures y degrees. The final angle in both triangles would measure. Okay, let me mark this up real quick here. So what I'm saying is let this angle measurement be x degrees, because we don't know exactly how much the angle measurement is. We're just doing this for the generic case. Let's let that be x degrees. So then what's this angle going to have to be? Oh, that's also going to have to be x degrees. What's this angle going to have to be? Oh, well, not have to be. Let's let it be y degrees. What's this angle going to have to be? It's going to have to be y degrees right here. Okay, so then the final angle, this one in red right here. So how could we deduce, if we knew two of the angles of the triangle already, how can we deduce what this angle must measure right now? What would we have to do? Say that this is 20 degrees, this is 30 degrees. What would that one have to equal? Well, 180 minus 20 minus 30, that's going to tell you your answer. So it would be 130 degrees right here. So anyways, it's obviously not that, but the idea is that each of these angles would be 180 minus whatever this degree measurement is here, which is y degrees. Well, we assign a variable to it, and then minus this degree measurement, which is x degrees here. So we have that for that angle, and then this angle right here, let's check it out here. This would also be 180 degrees minus x minus y. And look at that. We have the same exact measurement for these two angles. So both triangles would measure 180 minus x minus y degrees. So they would measure the same. And therefore, I'm going to do the therefore symbol. Is 3 dots here means the therefore symbol. Looks like a triangle. Therefore, measure the same. Therefore, they are congruent. Okay, so what I'm guessing you guys will probably write, because I wrote this a little bit more formally, I guess, with using variables. My guess is you're going to write, well, this follows because if you have 180 degrees in each triangle, and you got to say that, right? You got to talk about how it connects to the theorem, right? So you're talking about this, how it measures 180 degrees. Each one measures 180 degrees. If two of the angles are the same in both triangles, then if we subtracted those two angle measurements from both of the 180 degrees we have in both triangles, then we're going to get the same answer for the third angle, right? So you can say briefly, right? If we have 180 degrees in each triangle and we subtract both of the angles, which are the same in both triangles, then the third angles would be proven to measuring the same. So you can just wrap it up real quick. You don't need to use variables, but that's the idea, right? That's the idea. If we know two of the angle measurements and we subtract them from 180, we get another measurement. So if those two angle measurements are the same, then when we subtract it from 180, we are going to know that between the two triangles, if they share two angles in common, they're going to share the third, because we only have 180 degrees to work with here. All right, so that's number 7. So numbers 8, numbers 9, numbers 10 are going to be kind of more of the same of that. I think this is probably the wordiest one to word here. The other ones are easier, right? Like, how do you know an equiangular triangle measures 60 degrees for each of the angles, right? You just divide by 3. A triangle has 3 angles, and it has 180 degrees split amongst those 3 angles based on this theorem. So we divide by 3. Each one's got to represent 60 degrees. All right, check out this one here. This is going to connect to something that we're going to learn on Friday in your lesson on Friday, calls the exterior angle theorem. So let me write this down because I'm probably saying too much. This is when we see this exterior angle theorem, EAT. EAT is how we're going to name one of our theorems coming up. We're going to learn that on Friday. Don't worry about it right now, but what this is called right here. So notice here we have a triangle. Okay, we have a triangle right here. And if we extend one of the sides of the triangle, boom, right? This is an angle of the triangle right here. That's an interior angle of a triangle. Let's get rid of that. But what this angle is here, if we leave one of the sides here, we extend another one. I am running low on power. There we go. If we extend one of the sides, this is called an exterior angle. Okay, exterior angle. So I'm guessing you're able to figure this out without actually knowing the exterior angle theorem because you're able to deduce this. First step on this one that I think you would do at this stage is figure out what this is, right? We know that x degrees has to be supplementary to this here because the angle addition postulate tells us that that angle plus this angle equals 180 because the whole thing here is a straight angle, right? If we have a point here, point here, point here, this whole thing is 180 degrees, okay? So anyways, similar to this one right here, we start with 180 degrees and then we subtract 70 and we subtract 50 and that's going to tell us what this angle is. So 180 minus 70 is 110 minus 50 is 60 degrees. So this one here, x has to equal 180 minus that 60. And so that's 120 degrees. Okay. Hopefully you got that one. The purpose of this question is to show you that you probably already can figure something out here. Given two of the angles of a triangle, you can figure out the exterior angle of the triangle on the outside. Notice here, this is 120 degrees. What do 70 and 50 add up to? What do 7 and 50 add up to? Oh, interesting. Oh, interesting. So these exterior angles are related, right? Related to these two remote, these are called remote interior angles. You'll learn that on Friday. That's just a little bit of a preview. All right, number 20, draw the line through P and X parallel to JE. Okay, interesting. Guys, we have a theorem that allows us to do that. Well, we have a theorem that allows us, right? If this is JE right here, oops, line JE. Okay, so they show the segment, that's fine. The segment is contained by the line. So let's draw that in. Okay, it's kind of a sketch there. We know we have a theorem that tells us that through a point outside of a line, there is exactly one parallel to that line. Okay, so, right, if I draw on that parallel and it so happens to go like this, ooh, it didn't go through X. This is the one parallel, let's say, to JE, okay? And it didn't happen to go through X, okay? So I drew that out to show that as a reason because, right, we have one parallel. So I'm going to cross this out. Draw the line through P parallel to JE. Are you allowed to do that? Yes, you are allowed to do that, right? Through a point outside the line. Okay, so this question is, I forgot to actually say what this question is all about. So if you're just watching this here, please be reading the questions too. I think that's important. It says here, what's wrong with each of the following instructions? That's what you're saying here. So this is kind of this is a faulty instructions question. We got to explain why it's faulty. Okay, so I would say to this that we have a theorem, right? Theorem through a point outside a line, there is exactly one line parallel to a given line. Okay, we have that as a theorem. So that means that we know that this parallel through P, that's parallel to JE, it exists and it is unique because we have this exactly one statement in here, okay? So it exists and we know there's not going to be more than one, right? There's not going to be more than this one line. The problem is this one and only one, this exactly one line, is not guaranteed to go through any other particular points. It's not guaranteed through X. Does it look like a parallel would go through X? Well, probably, right? Based on the fact that this point X is made really, really big here. But remember, points are infinitely small. They're tiny, infinitely small. So the odds of the line going through point X are infinitely low, right? Infinitely low here. So the way I would justify this is our theorem above does not guarantee that the unique, I'll do it this, with the unique is we have exactly one, the unique parallel to JE through P would pass, right? Would pass through any specific points. Right? We don't know. right? We don't know if it's going to go through point X or not, though. We can't dictate that based on the fact that we just drew in a parallel. It's like, oh, magically it's going to go through this point that's already on our diagram. We could draw the parallel and say, and then add a point to the line. We would know that that would have to exist because points are made up of infinitely many lines, but we would not know if this line actually went through that point X here. So this would be what I would go through and answer. Email me if you have questions on that. I know this is similar to one on the exit ticket that we're kind of confused by. So anyways, we'll check it out here. All right, 2 more problems with you guys here. We got, this is number 14, and then we got number 31, which is a proof. So let's do these ones together. Find the values of X and Y. Let's check it out. Let's do this. Oh, what do we notice here? We have parallel lines. So here are parallel lines. So we have some potential transversals here. We have a transversal here. We have a transversal here, and that's about it. So it looks like here, because these transversals, our lines don't, or line segments aren't going further than this. So my guess is this problem might have to do with same side interior angles here. X plus Y plus 100 would equal 180, right? Because those would be same side interior. We don't really have alternate interior angles going on here. Don't really have them. These are not alternate interior angles because let's see. Yeah, actually, this is an alternate interior angle to that. That's true. That's true here. So maybe alternate interior angles are involved. We don't have corresponding angles, though. That's what I was going to say, because we're not above the transversal or anything like that, or below the transversal here. So no corresponding angles, but maybe alternate interior. Okay, so what do we notice here? Maybe let's deal with this first transversal and maybe make an observation here. So there's a transversal crossing, okay, parallel line here, and the parallel line here. Sometimes it helps to extend them. You can see it a little bit better. Fruit fly right in my face here. Okay, so we know that this angle X here is going to be congruent to this angle. That could potentially help us. So maybe I'll mark that up. Okay, I'll mark that up. 50 degrees, that's going to help us at some point. Ooh, look, I remember this one. It's nice, tricky. We notice this one here. What's this symbol mean? The symbol means 90 degrees. Okay, 90 degrees here. So we know that this triangle, maybe that's why marking up's important, because you notice things. I know that this triangle here that I'm shading in red right here, okay, this triangle right here in red is going to have 180 degrees in it. That's what this section's all about. So you got to deal with this 180 degrees number for sure here. So I know that X degrees plus 90 degrees plus 50 degrees is going to add up to 180. I know that from theorem 211. I know that I don't say the numbers, but we just dealt with theorem 211, right? The sums of the measures of the angles of a triangle, and that means interior angles of a triangle, adds to 180. So you add 50, add 90, and then now it's as simple as that. We can solve for X. Combine like terms, this is 140. X degrees plus 140 equals 180. Subtraction property of equality. We subtract 140 from both sides. And yoink, yoink, 40 degrees equals X. Okay, so X is 40 degrees. And now that we have this, ooh, okay, so I did this earlier. I didn't explain it, though. But the thing that I did in purple, okay, right here and right here, okay, these are alternate interior angles. Cut by parallel lines in a transversal. Okay, parallel line, 2 lines, and this is an angle, this is an angle. It shares this transversal right here. So we know that this is X degrees, that's X degrees. So we're going to know that out of this other triangle, this is 40 degrees, and that's going to help us find Y. That's totally going to help us find Y. I mean, we could also done it here, right? These are just supplementary. If this is 40, this is also going to have to be 40. But anyways, I'm going to set it up with this purple triangle right here. Okay, we got our purple triangle right here. So I'll set it up. This is X degrees. That's Y degrees. We know they're going to add up to 180. And this is going to be 100 degrees. Plus, instead of writing X right here, I'm going to write what X is equal to. Okay, which is 40. And then I'm going to add Y. And this is going to help us solve for Y here. Okay, 100 plus 40 plus Y equals 180. So again, the same deal, right? This is the same exact problem we had really above us here, except this is Y, not X. Y plus 140 equals 180, subtract 140 from both sides, and 40 degrees equals Y. You are good to go there, my friends. Example on that one, good little puzzle. I think people like those problems when they get them at least, right, to get through. All right, people love these problems right here. We got a proof, my friends. That's right, it's a proof. Let's do this. I got my Phil's coffee. Oh, here we go. I told you it's morning. Thursday morning. What better day to do some geometry, my friends? Puzzles, babies. You like puzzles, you like this class. Let's do it. Anyways, I don't mean like jigsaw puzzles, these are puzzles, right? And see, I have trouble sleeping until I get this thing, right? You want to figure these things out. So let's check it out here. All right, reminders. What you have to do, you have to write your givens and proof statements here. You have to draw the diagrams because those ideas, they start flooding. We don't like stay on our heels. We don't like, I didn't really get this far on this. Guys, just copy it down. Copy it down. That's good. Turn it in if you like really have no idea how to get started. That's fine. But I hope you at least know the first step, right? First step, okay? Because I want your ideas to start flooding with you. The world's best mathematician a few years ago, Mira Mirzakhani, she drew things. She gets down on the ground here and she climbs up to that hill and she sees things and they're more clear because of that. And art and drawing is a perfect way for her to unlock the mysteries of math. And this is what I hope you to unlock here. Okay. We have some gifts from the math gods. We have some given premises. We have the given diagram. And then we have something that we're going to prove. So maybe I'll mark up what it is I'm trying to prove here to keep me focused, right? Keep me focused, keep me organized. This is what I'm going to try to prove. So I'll put a little question mark on top. So I know that ultimately my goal is if I can maybe get alternate interior angles congruent, that could help. If I can get, there's potentially some corresponding angles. If I can get angle H congruent to angle JIIGK, that could help too. So see, by marking up, I'm making observations of things that could help me. It looks like I'm given sort of in the given premises something about angle H. That's helpful. So now I'm going to shift my attention to given premises, actually. So I'm going to mark up, okay? Mark it up is a great way to figure out what's given to you, what's handed to you from the math gods, so you can potentially arrange your reasoning and prove this statement here. If GK bisects angle JGI, so here we got JGI here, so I'm going to know that this is congruent to that because of definition of bisects for angles, that those two are congruent to one another. I'm also given that angle H is congruent to angle I. Oh, that's nice. Okay, so let's do this here. I'm going to do that in 2 tick marks because I haven't connected these yet. Okay, that's a given premise to me too. Perfect. Let's do this. Okay, so now let's do that. Last part of the step is proof is to actually write the darn thing here. Got my statements here. Got my reasons. Step 1, let's get the given premises down so we can actually talk about them, use them in this proof. Ray GK bisects angle JGI. And measure of angle H equals measure of angle I. It's nice they give us the measurements rather than saying the angles are congruent, because using measurements, you can add them, you can subtract them, you can say they're equal to things, right? Which is better than just congruency. You can't subtract congruent shapes. What's subtracting a shape? What the heck is that? Anyways, given premises are there. Okay, so I think we want to get that angle congruent to that angle. So we can do that one of 2 ways. It looks like if we can get angle H somehow congruent to angle JGK, that will get the job done for us. Because, right, check it out. This line here and this line here, those are the 2 lines we're trying to get parallel. And we have a potential transversal right here, line JH. Okay, and then these would be in corresponding positions, right? They would be in the top right position, right? In the intersections, in the angles that get formed by the transversal. We also have another transversal, right? We have it right here, okay? And this transversal, on the alternate sides of the transversal, we have interior angles. So if we can get angle 2 congruent to angle JGIH, then we're good to go as well. Because then we would have established if we have 2 lines cut by a transversal and alternate interior angles are congruent, then the 2 lines would have to be parallel. So that's kind of what we're practicing on this too. All right, let's figure this out. How do these connect? These are congruent to one another. Very nice. They are congruent. How are we going to get that congruent to that? Or how are we going to get that congruent to that? Let's think. What can we do? I don't know about this one. This one's tricky. Tricky. Do you have ideas? Let's hear your ideas. Okay, I messed up here. I got confused because, check it out, I actually copied down this wrong with tick marks here. So hopefully that didn't betray you here. We're given H is congruent to I. Nope, I didn't actually screw that up. These are bisected. What are we going to do? Wow, Mr. Fortin kind of stumped on this one, to be honest. Let's check it out. Let's see here. Well, these aren't connecting. I remember even this one because that was actually a trickier problem than I thought it would be. JG bisects JGI, and H and I are congruent. So back to here, here's the section.